Okay, so the first problem that we can discuss today, before going to the graph algorithms again. Okay, so the one outline of this problem I'll be discussing. Okay, and the lecture notes I'll be providing, and you go through this problem. Okay. So this is the majority element finding problem. So you are given an array A. So,
Please share
oh,
the screen.
yeah, yes, yes. Okay. So this is majority element finding, and what is that problem? Okay. So let us take this array. Okay. And okay, before going to this, this majority element having many applications in today's world. Okay. This is one of the very hot topic of research right now. Okay. So this comes in everyday life with say Amazon and other companies. How it is coming, this majority element, is that say we have discussed in the introduction class that okay, let us say that Amazon having many products, okay, many product search. The people are coming and searching the products, and Amazon say for example, say this is some kind of chair, and this is a camera, right? And so on. And each time a chair is searched, Amazon is incrementing its count. Okay. Each time a camera is searched, Amazon is incrementing its count. So at the end of the day, say chair might be searched, chair. So at the end of the day, say, or instead of incrementing, incrementing means we can think of for understanding the problem. We can think that say chair is first time searched, then say camera is searched, then again a chair is searched. Okay, then again a camera is searched, then again chair is searched. Say say next say one shampoo is searched like this way. Okay, and then say again a chair is searched. So at the end of the day, you see, if chair I am representing by 1, say camera I am representing by 2, and shampoo I am representing by 3, then this array is becoming this array. So instead of writing it vertically, I can write it horizontally like this. So this is first time chair is searched 1, then next time camera 2, then next time chair is searched it is 1. Okay, next time camera it is 2. Okay, next time chair it is 1, next time shampoo 3, next time this camera this chair 1. Okay, so you see this is 1 1 1 appearing many times. Okay, so how many times if it appears, so if it is appearing more than n by 2 floor, more than this, or we can say this n by 2 n by 2 okay, first of all let us take more than n by 2 floor number of elements, if one is having this n by 2 floor, more than n by 2 floor number of times it is appearing in the array, we will be calling that this one is majority. So this 3 and 7 elements we are having. So 7 by 2 floor is how much? Can you tell me? 7 by 2 floor,
Three, sir.
3. Who is telling?
136, Ashutosh.
Ashutosh. Yes, 3. So in this array, if I am having some element appearing more than 3, that means 4 number of times, right? 4 number of times. Then we can say that this element is the majority element. Okay? And this you see the connection between this majority element and the product search at the Amazon. Okay, right. So Amazon is little bit generalizing this problem. That means, say, they are telling it as a K heavy hitter problem, heavy hitter. Instead of checking one majority element, that means heavy hitter. Majority element means that those products are searched heavily. Okay. So instead of finding one heavy hitter, maybe say chair is searched 1 million times, camera is searched 500,000 times, okay, per day. So we can think of camera and this chair, both are, say, in that case, Amazon will be trying to find out two heavy hitter problem. K heavy hitter means two of the most searched product Amazon will be trying to find out, right? So this is the problem. And the thing is that how to proceed. Okay. The algorithm for one majority element, okay, may not be good for this in general K heavy hitter problem. So the K heavy hitter actually is the modern day application of data science problem. This is the K heavy hitter problem, and a probabilistic data structure called count mean sketch is necessary for this. That is not there in our syllabus. But if I, why should I find out the majority element? One of the application could be this. Okay, and this is absolutely a modern day application. Everybody who is thinking that he is a contender, he or she is Amazon, Google, Facebook, whatever, okay, Microsoft, then they should know the majority element finding algorithm. Okay, right. So this is the problem, and you have to go about it. Okay, so this the brute force manner. That means I am counting how many times each element appearing. Each element I am uh, taking the fact that each element how many times appearing. So I am taking each element and then I am comparing how many times. So each time I am taking one element, I have to search through this list, to this array, to count how many times it is appearing. If I am taking this guy, then how many times it is appearing, then again I have to search the list. So it will be ultimately giving order of n square time algorithm. Okay. Now can we improve on this? So maybe this median element is in the majority part. Okay, so we are finding the median. Okay, we are finding the median. Uh, Extract this and count its frequency. Then again, I have to check. Okay, this I am finding what is the median of this list, and then if I am finding one, maybe if the all elements are distinct, we will be finding also one median. Okay. But at that time, median will not be the majority element. So if it is repeating, then we can find one median, and then we have to count how many times it is appearing. So to whether it is appearing more than n by 2 floor, or say n by 2 ceiling number of elements. So then we have to again search this list. Okay, that will be taking order of n time, and finding the median by the kth smallest element. Kth smallest element finding, we know it will be taking order of n time. Order of n time plus order of n time, it is order of n time. Okay. So this is order of n time algorithm. Again, we are finding. Is there, but the thing is that finding the median with kth smallest element is lots of hidden constant is there. Okay, we have seen that complicated algorithm, right? Now, is there any other way to do it? Okay, complexity wise, even if it is not, even if I am not beating the order of n time, but we don't want the hidden constant which is there in median finding. Okay. So this is, I give you the hint, and I'll be suggesting that you go through these notes. Okay, you'll be getting. Okay, because time is short, so that's why I'm not discussing at its full length. Okay. So here you see, if you see this list, then can you tell me that is there any majority element here? So one is the majority element. One, one is the majority element. Sorry, which one? So one is the majority element. One is the majority element. Who is telling? Sir, rule 172. 172. So one is the majority element. So if you observe that okay, ultimately one has to be survived. Okay. So now a method of induction we can use to design this algorithm. That means say 1 and 2. So this 1 and 2, if 1 is there, okay, I can think of this is the majority element. But when 2 is coming, then they are having the ties. That means we can think of that, okay, no, I will be incrementally approaching the problem. That means I'll be, first of all, I'll be thinking that we are having two element array. Then I'll be thinking that, okay, I am having say after this I can start, so this part is over, then I can start from here to here. Okay, like that, or I can start from here to here. So you see, if I am thinking 1 and 2, these two elements are there as I am going through incrementally. If these two elements are there, these two elements, neither of the elements will be can be the contender of this majority element, because that criteria, more than n by 2 floor number of elements are there. Because you see, at that time you can think of that 1 is being knocked out by 2, okay, to be the contender for majority element. So you see, we can think of 1 and 2 have been knocked out each other, have been knocked out by each other. Okay. And then maybe we can think of, say, we can start afresh the problem, and maybe we can think of that whether the next remaining part could be the majority, could be the contender of this majority. Maybe whether we will be starting from 2 or afresh from 1 to 3. So let us assume that we are starting 1 again afresh. We are thinking 1 and 2 are not there because they are knocked out. Okay, 1 and 3 is there. 1 and 3. The next one will be considering, and that will be thought of as the majority element. Then when 3 is appearing, then 1 is knocked out by 3. Okay, so we can think of that. Okay, this pair never appear. Then one is remaining, and that is the majority element. Okay. So this idea can be used for finding the majority element. Okay. And what we are doing is here, why we are telling that this is by the method of induction, because we are incrementally we are proceeding. Okay, we are thinking that okay, we are having the two element array, then we are starting afresh. Okay, so we are not taking the whole element, we are incrementally proceeding. That means the method of induction is that okay, for lesser values of n, something is true, then for higher values of n, something will also be true. Okay. So that incremental fashion we are taking here. So that means a method of induction technique we are utilizing here. Okay. But the thing is that this is the major observation that okay, one is there and then again another distinct element is coming, then that means that distinct element is cancelling out the previous element to be the contender of the majority element. Okay. So that observation will be leading us to algorithm. So here one example is given. So I'll be posting this lecture notes, okay, and you go through it, okay. And this is important, okay, for exam purpose, for application wise. So this is important. Okay, today I'll be proceeding little bit fast, okay. So this is for this majority element. Then we'll be discussing what I told you, that the application of depth first search will be having today. That we'll be having definitely. And before that, okay, we are having one more, that is all pair shortest path. Okay. So this is the all pair shortest path. So this all pair shortest path problem, from the single source shortest path, we are taking a source vertex, and from there we are trying to find out the shortest path from all other nodes. Okay, that is the single source shortest path. Source is fixed. Now the problem is, say I am considering the shortest path from here, all the nodes. Then if I am fixing this is our source, then what is the shortest path of all this? So one of the ways you can think of this problem, that okay, we can run the number of vertices, how many number of cardinality of v times I can run the single source shortest path. Say first time I am fixing this and I am running single source shortest path. Then the next time I am fixing this node as the source one, and then I am running the single source shortest path. So likewise, we can run cardinality of v number of times the single source shortest path, and we can get all pair shortest path. That is one way. Okay. Another way is that we have to use this dynamic programming solution. Dynamic programming solution, right? So in this, the philosophy, the dynamic programming. Okay. So from here to here, whenever I am trying to find out some kind of solution from here to here, then what I am doing, I am thinking that okay, I can subdivide this problem. I can subdivide this problem into two parts like this, these two parts in this position, say k, or I can subdivide the problem in these two parts, say k may be here, I can have the subdivision like this, these two parts, and so on. Okay. And then out of all this subdivision, which k is giving, which k is giving the solution, the minimum solution. Say if it is a minimization problem, which k is giving the minimum solution, that k, I am taking into consideration. Okay. That means to find out the optimal solution of this, that k position will be the best one to divide that problem into sub-problems. Okay. And here what we do actually in dynamic programming, okay, say we take some kind of say bottom up approach. That means if you have got this matrix chain multiplication, so we are thinking we have got say a1, a2, a3, a2, a3, a4, a5. So this is the chain of matrices. Then what we think that, okay, let us suppose we are having chain length 2 matrix first. And then we have to find out the optimal solution where to cut these two in between. Then I'll be considering the chain length 3. Okay. And whenever I'm considering chain length 3, say I can have cut like this, a1, and then a2, a3. So here I can cut, or I can cut here. At that time I am solving a1, a2, and then a3. So out of these two, which solution will be giving the number of multiplication is minimum, that solution I'll be taking. So chain length 3 is considered, then I'll be considering chain length 4. And whenever I'm considering chain length 4, say maybe I can cut here. Okay. I can cut here, and then a1, a2 I have to take into consideration, and a3, a4. So now you see a1, a2 already I have considered a1, a2. A1, A2, I have already considered here or previously whenever we considered chain length. That solution is ready for us. That solution is already stored. Instead of computing this, what will be the optimal solution for this? I have already computed that. And that stored solution I'll be utilizing whenever I'll be taking, say, chain length 4 or chain length 3. Okay. A1, A2 is already computed. So that is the main philosophy. We are storing the previously calculated solution in table, and then that optimal solution, if required afterwards, we are utilizing that. Okay. Otherwise, if I don't do, if I every time if I afresh solve the solution, then it will be running in exponential time. Okay. So that is the main philosophy of this dynamic programming. Okay. So that is the overlapping subproblem criteria. So now you see this all pair shortest path. What I am doing here. Okay. So first, say this thing, this this matrix we have to first form. Okay. How to form this matrix from whatever path cost we are having here? From there, we have to find out this matrix. Okay. So this maybe we can think of index 1, 2, 3, 4, and 5, and here 1, 2, 3, 4, and 5. Okay. So 1 1, you see 1 1 2 2. That means we are not moving this node, so it's zero cost. Okay. And you see 1 2, okay, 1 2, 1 2 having a direct path, and its weight is 3. So I have documented here as 3. Okay. And then this 1 and 3. Okay, so 1 and 3, you see 1 and 3 also having a path, and its path cost is 8. So 8 is documented here. Okay, so like this way, and say 2 and 1. So 2 and 1 not having any edge directly, so I have put a large cost over it, large cost for it, that is infinite. Okay, large cost. So like this way, we have to fill up the initial matrix that we are denoting by D0, initial matrix. So this initial matrix we are initializing with this path cost that we are having. Okay. Now for say now what I am trying to check. Okay. So now I am trying to check that, okay, if I am taking, say, if I am finding, now I'll be trying to find out D1. That means, so this is like the shortest path. Once I have discovered one, then I have to relax this one. Okay, so that relax procedure is coming. That means via this one, is there is there paths, is there path uh, that is there for other nodes, okay, to some other nodes. Uh, Say you see 1 and 4, 1 and 4 not having. So first one is discovered. That means we are going via this one. Okay, so this D1 means we are going via 1. Okay. Now you see 1 and 4. What is the what was the path cost whenever we had this D0, 1 and 4. So this 1 and 4, you see we are not having any kind of connection directly, so it was infinity, right? It was infinite. And say this 4 to 2 to 4, 2 to 4, what was the cost? Sorry, 4 to 2, what was the cost? 4 to 2. Can you tell me what was the cost of 4 to 2 here? 4 to 2. Can you tell me what was the cost of 4 to 2? From this graph, you can check and you can tell. You don't have to check this D0. You just check whether 4 to 2 there is any direct path.
No, sir, there is no direct path.
So what was 4 to 2?
Infinity.
Infinity. So 4 to 2, 4 to 2, we are having infinity here. Okay. 4 to 2, right? So now you
Yes.
see that this one,
Sir, excuse me, who has answered this? Can I know?
so you mute yourself. Okay.
Sir, actually, who answered it?
Uh,
May I know?
who answered this question? That
Right. Sir, Subrata.
Subhrata Pal. Okay, what is the
Yes, sir.
roll number? Okay, okay, okay.
39.
Okay, sir.
uh, okay. So now you see this. Whenever I have discovered this one, okay, and whenever I am feeling this D1, okay. So at that time, 4, say I am considering 4 via 1. Is there any other path to any other vertices? Okay. So I am seeing that, okay, from 4 to 1 and then to 4 to 1 and then 1 to 2, I am having a path. But previously you see that 4 to 2, we didn't have any path. Okay. 4 to 2, we are not having any. But once this 1 is discovered, that means via 1, I am trying to check via 1, I can reach from one vertex to some other vertex. There is a path. Okay. So now you see, if I consider D1, and then 4 to 2, if I am 4 to 2, if I am checking, so this is our D1 and this is our 4. Okay, this is our row 4 and this is our 2. 4 to 2. So 4 to 2, you see, via 1, how can I reach 4 to 2? This path having cost 2 and this path having cost 3. So 2 plus 3, 5. So now previously 4 to 2 was infinity. Now it should be updated with 5. So let us check this D1 whether it is updated with 5. Yes, it is updated with 5. Okay. It is updated with 5, right? So like this way, we have to update all the elements, okay? So now you see, uh, whenever I am considering D2, okay, so this cost is not updated. This cost will be remaining same because 4 to 2, that was infinity. But via 1, I can reach 2 with a less cost. So that is getting retained, right? Now you see this here in this D3, that means via 3, I can reach. I can reach to 2 via 3, okay? Via 3, I can reach to 2 with some other cost from 4. Some other cost from 4, right? So now you see the cost is updated as -1. So you see 4 to 3, I am having a cost -5 and 3 to 2, I am having a cost 4. So if I add this, then -5 plus 4, then it is coming -1. But previously I was reaching in a shortest path via 1 to 2 and that cost was 5. Now as I am taking this dynamic programming, so you see dynamic programming is coming into picture. So you see this 4 to 2, 4 to 2, I am having several such path, say several such k. So this is k, one k, this is another k. Okay, so just like this, as if I am finding the shortest path between these two, and I am checking, okay, via some other vertices I can reach. I am having several such things, and previously I computed, say this is via 1, this is via 1, and this is via 3. So previously I have computed that is 5, and now I am computing via 3, and that is -1. The minimum of this I am taking into consideration, and that is -1. So that's why it is updated with -1, right? So I have to also check that whether I can reach from 4 to 2 via 5 or not. If I can reach with a less cost, then that cost will be updated again. Okay. So, but I guess that it will not be updated. So -1 will be retained because at that time I don't have any path from 4 to 5 directly. So it will be always infinity. Okay. So via 3, whatever I am getting, that is remaining updated, and that will be retained throughout. Okay. So you see, this is via 4. Okay, via 4, 1, and 2, I am checking. Okay, so this I have to do for all the vertices and for via all these. Okay, so whenever D1 I am calculating, then from 4 to 1 to 2 I am checking, from 5 to 1 to 2 I am checking, from 3 to 1 to 2 I am checking. So all these I have to check and I have to update this D1 table. I have shown one, you have to complete this. Then again, whenever whenever I'll be taking this 2, D2, okay, so this D2, that means 1 to 2 to 3 I have to check, 1 to 2 to 4 I have to check, 1 to 2 to 5 I have to check. Okay, so via 2, can I reach some other vertices with a less cost? That is the thing. Okay, so you see this Dijk, okay, Dijk, that is telling that, okay, so this 4, the Dij means, say I am trying to check 4 to 2. Okay, D 4 to 2, 4 to 2 via 1, 4 to 2 via 1. Then I can check it that at that time, say the previous k, so that was k minus 1, that was 1. Okay, so 4 to 2 via 1 I am checking. 4 to 2 via 1 I am checking. So this is this is Dijk minus 1, previously computed 1. Dijk minus 1, that was previously computed was infinity. And now once this 2 I am checking, so k minus 1 is 1. So that means via 1 I can reach to 2 with a less costly way or not. So D1 to k, D1 to k, that was what? Can you tell me? D1 to k, D4 1 1 4 1 1. So D1k, that means this is Dik, okay? This Dik. So what is uh, I here? Say I is 4. Say I is 4 and j is 2. So this is our j. J is 2. I is 4. And then I am dividing the problem into two parts by considering one intermediate vertex, k. So I is 4 and k is 1, right? So 4 1, what is the cost? Can you tell me? 4 1, that I'll be getting from this table. Okay. And from this graph also I am getting 4 1. What is the cost? Who will be telling? Who will be telling? 4 1, this is a very simple. Nobody is listening, I guess. 4
So
1, what is the
4
cost?
to 1 will be 2. And so 4 to 2 via 1 will be 5.
And this dkj, k means 1, j means 2, and this is k minus 1 means 1. So I'll be getting from this previous table. That means directly from here also I am getting 1 to 2, 1 via 1, uh, or whenever I have discovered this one. So D12 from this table, previously computed table, I'll be getting it is 3. So 2 plus 3, that is 5. So that's why it was updated with 5. Okay. That's why it was updated with 5, right?
Yes, sir.
So this is the way this is the dynamic programming expression. The minimum of whatever previously computed and whatever the via path I am computing. And this will be iterated for all such vertices, okay, for k equals to 1 to n. That means all such k, so there might be another k, there might be another k from here to here. So all such k I am considering, and over a period of all such iterations, the minimum one I'll be finding. Okay. So this is the philosophy of all pair shortest path. You complete the other tables and all these entries, and these are the parent pointer that I am not discussing. You go through it. Okay. May not be necessary for the exam, so you can omit this. But if you are inquisitive, you can go through this, how this parent pointer we are maintaining. Okay, so this is the all pair shortest path. And now we'll be discussing this what this the Dijkstra's depth first. I mean the depth first algorithms application. Okay, one such application is we are having perhaps here. Hmm. So this is the strongly connected component. Say we can have some. So this first of all, let us take this. So what is this strongly connected component is? So say I am having a graph, say like this, and say from here to here, and say from here to here. So you see, here every pair of vertices u and v, which is a in C, which is a subset of this v. Okay. We have both u to v connection and v to u. So this is telling, with this notation is telling that okay, we may not have any direct connection between u to v, but maybe we can have some via connection. Say for example that from here to here we are not having a direct uv connection, but we are having a via connection. We can reach from u to v, okay, somehow, right? And also v to u we should be having. So if this is our u, so here I am having how many such vertices u, v, w, x. So we are having this v equal to u, v, w. So these are the 4 vertices I am having. And C is a subset of these vertices. Subset of these vertices. Say I am taking this portion of the graph, okay, and that is consisting of this C. C is here. We are having U, V, and X. U, V, and X. So these vertices I am having as C, and this is our V. So C is a subset of these vertices V. Okay, I think it is clear. Now, if I am taking this C, now whether this condition U to V for every such pair UV in this subgraph, which is comprising of these vertices, having U to V path and V to U path. If that is, then we will be telling that component is strongly connected. Strongly connected. Now, can you tell me that this portion, what I have segregated U, V, and X, is it strongly connected?
So V and X.
V and X?
Yes, sir. V and X is strongly connected.
V and X. This component graph, this is the graph I am having. This subgraph, is it strongly connected, consisting of vertices U, V, and X? Is it?
Sir, there is a path from V to X, and sir, from X we can go to U and then V. Sir, then will it not be considered strongly connected?
So this subgraph that I have considered now, this subgraph, okay, this is strongly connected because every pair, if I am taking, say U and V, I am taking, then I am taking U and V, I am having a direct connection, and V to U, can I reach from V to U? Yes, I can reach. Then
Yes,
I
sir.
am taking V and X. So V and X I can have direct connection. X to V I can reach via U. And then X to U, I can reach X to U directly. And then uh, U to X, can I reach? U to V and then X. Okay. So this subgraph is strongly connected. Now, if I am taking the full, that means this total graph. Okay. So is it strongly connected? That means the total graph,
No,
if I
sir.
am considering C consisting of UVX, UVWX, is it strongly connected?
No, sir.
Huh?
No, sir.
Who is telling? No.
Sir, if you are including
No.
W,
Who
then
is
sir, it is
telling
not.
no?
Sir, I.
Huh?
Sir, I.
Huh? You are right. Who is telling?
Sir, Aditya Singh.
Huh? So this you see this from W and V, I can reach from W to V, but can I reach? W to V I can reach. Can I reach from V to W? There is no path. So this path is blocked. This path is there is no path, no such path. Okay. So V to W I cannot reach. So if I am considering the total graph, this is not strongly connected. But if I am having this is one strongly connected component of the graph, and this node alone, this node, if I am separating, so I am separating the graph with consisting of these nodes, and I am separating this node. So this node alone, as this is still alone, so this is by default strongly connected. Okay. And this subgraph is strongly connected, right? So this is the definition of strongly connectedness, right? And here in this graph, I am having say this portion. This is from CLRS. So this portion is strongly connected. So this is another portion which is strongly connected. Another portion which is strongly connected. Another portion which is strongly connected. So this is the definition of strongly connectedness, and here is the algorithm for strongly connectedness, strongly connected component. So what we got to do is here, the idea is okay, call DFS. So call DFS to compute the finish times u dot f for each vertex u. So from here you see in this graph we have run DFS first. This is called Kosaraju's algorithm. Okay. This was sometime it was unpublished, but later it was discovered that it is first it was discovered by Kosaraju. Okay. So first I am running DFS, so maybe I can start with this, that is 1, and then it will be searching its neighbors, say this is this guy, and this is the start time 2, and then it will be going here. Okay, with this DFS technique, then it is 3. Okay, the start time, right? So now you see from here I cannot move here, I cannot move here. So I have to end this searching here. So this will be at that time blacken, and it will be ended with this finish time 4. Then I'll be coming back here. Okay, but here I, I am having another way to go. So it will be 5. I'm going here. Okay. I'm going here, and then it is 5, right? It is 5, and then from here I am not being able to go. So it is ending time is 6. Then I'll be coming back here, no other path, it is 7. Okay. Then I'll be going here, but I can go from here to here, so it will be 8. Then I am not being able to go anywhere because this path already explored, I mean this node already explored, so it will be finish time 9. Then I'll be coming back here 10. Okay. Then I cannot go any other. But then I'll be going back to the main loop, and then I have to start all over again from here. So it will be 11, and then already this is explored, so I have to explore this 12. Okay, then 13, then no way. So finish time 14, then 15, and then 16. Okay, so this is the DFS algorithm. If we are doing, then this will be the start time and the finish time, okay, for every node. Okay, then what we got to do is we have to compute this G transpose. So you see we have to compute G transpose. G transpose. Now what is the meaning of G transpose? G transpose meaning that, okay, this is the original graph. Okay, so this is the original graph. An original graph, if this is a forward direction, we are having a path. In the G transpose, we will be having the path is reversed. Okay. So this will be done for every such pair. So path is reversed, right? Here it was in this direction, but here it is in this direction. Here it is in this direction, so here it will be in this direction. So this is our G transpose. Okay. So this is our G, graph G. Okay. And now, uh, call DFS in this transpose graph GT. Okay. Consider vertices in decreasing order of U dot F. Okay. So uh, here the finish time is the highest finish time of all this node. Which node having highest finish time? Can you tell me? Here in this graph, which node having the highest finish time? Is it this node? 12 is the start time, 15 is the finish time here. So which node having the highest finish time?
B. Sir, not.
This one,
Yes, sir.
this node B.
Yes. Yes, sir. Not B.
Huh. So you see, I have to consider forming the DFS again from this node. Okay, U dot F. U dot F. So here the idea actually why we are computing G transpose. So first is G transpose. We are running DFS in this graph G. That means we are checking whether there is a path from this to this, U to V. And the G transpose, as I have reversed the edges, then here in this G transpose, will be a decreasing order. I am checking, so U to V. So from here I am reaching, and then from here I have to start. So decreasing order, I have to find out, I have to run the DFS. So here the two things happening. That means why G transpose we are doing, because I want to check that if there is a path from U to V, a path from V to U, a path from V to U, so may not be direct. A path from V to U, we should be having or not. We are having or not. Okay, right. And this finish time is ensuring that we are starting from uh, as I have reached from U to V. So V is our point of finish time or point of finishing line. Then I am starting from the finishing line. So this is how the philosophy of this strongly connected component using DFS is working. Okay. So in this case, you see so I have to run DFS from here. Okay. So now DFS, I am having this one here. I can use the red pen, one here, okay. One here. And then I have to follow this DFS, two here. Then I can follow this 3 here. Now, can I go from 3 to any of the nodes further? Can I go from here to here? Can I consider that? Can I consider this 3 to 1? Once
Yes,
I
sir.
have reached here, can I consider this? Can I consider again? This is a lucrative path because once I have discovered 3, I can reach. But should I consider that? Nobody is studying at all in the hostel.
Sir, we can. So from 3 to 1 we can go, sir. But in step 3 it is written in order of decreasing you, sir. So then we can go from 3 to 1.
No, no. Oh, you forget about this. Once I have reversed and I have encountered this, that this is the decreasing order, then I'll be forgetting that whatever value we had there.
Yes,
See,
sir.
now you are coming back to the DFS. So 1 and then I'm having 2 here, then I'm having the depth 3. Then can I from 3, I am having a path, but should I explore that path or not? What
Yes,
is
sir.
the, what is the condition?
So it should not have been already visited.
Ah, who is telling?
Sir, I the testing.
So this is already we have explored. Okay, so that is great. So that means from here we can explore those nodes which are still white. Maybe this guy, maybe this guy. Okay, still white. Right. So once I have done this, now uh, I so you see this thing still not great. Okay, so this is white. Anyway, so this node I cannot explore from here to here because there is no path. So I have to end here 4 and then I have to come back here. I cannot go anywhere. So this is 5 and then I have to come back here. I cannot go anywhere. So this is 6. Now you see this this tree. I am forming this tree. Okay, this tree. So this is the tree that is indicating that I am having a path from V. So if this is V, this is U, I am having a path from V to U. Okay. If I am having a path from U to V, okay, then I am having a path from V to U. So this is how the Kosaraju's algorithm will be working. Okay. So output the vertices of each tree. So this one tree will be formed here. Uh, say one tree will be formed here. One tree will be formed here, right? So one tree will be formed here, and this is alone. So that means the philosophy is we have to compute G transpose, and also G transpose will be running DFS, and at that time it will be ensuring that if I am having U2 V path, then if I am having V2U path also, then it will be correctly finding. Okay. So we are not proving the correctness of this algorithm. We have intuitively understood that okay, uh, we are trying to find out the strongly connected component means U to V path. I am having U to V path. Then I'll be also checking whether V to U path existing or not. So that G transpose every in the G transpose I am reversing the age. So this U to V path existing or not, that will be ensured. So intuitively we have done the correctness, but there are mathematical ways of proving that okay this Kosharazu's algorithm will be absolutely correct. Okay. We are not going to this if it is coming in the exam. So if you are writing whatever I have discussed, so you'll be getting the marks. Okay. Okay, so do you have a class after this?
Yes, sir. We have an exam today.
Okay. Okay, so today up to this, tomorrow I'll be taking the last class where I'll be discussing this approximation algorithms. Okay, you can, I mean, Noreen, you take the attendance.
Yes, sir. Yes, sir.